So welcome to my class on Introduction to Statistics as you may know it in your school, STA 1101. In this class, I will be looking at solving questions from a certain year, okay? So we'll be looking at past questions. Quickly, let's go with question 1. So question 1 says, define the term statistics as a subject area. As you can see, question 1I. So statistics, to answer that question, okay, question 1, statistics is defined as a science or branch of mathematics that is concerned with collecting, organizing, describing, analyzing, and interpreting numerical data. So that answers question 1I. Let's go to question 2. Question 2 says, describe the major difference between discrete data and continuous data. Now let's come over to the board. So the difference between discrete data, I'm going to put here discrete data. I'm going to separate that with a line, and I'm going to put over here continuous data. So what is the difference between discrete data and continuous data? The major difference. Discrete data are data obtained by counting. So you can see I'm putting that in uppercase letter. So what makes discrete data different from continuous data is the fact that discrete data is obtained by counting. However, continuous data are data obtained by measurement. And that answers this question. So let's go to question 3. It says, explain any 5 graphical techniques for describing numerical data. I'm going to mention all the graphs, as many as possible available, and we are going to describe or explain 5 of them. So I'm going to start with the pictogram. Okay? B, I'm going to mention the line graph. C, I'm going to mention the box plot. D, I'm going to mention the bar chart. E, I'm going to mention the histogram. F, I'm going to mention the pie chart. G, I'm going to mention the frequency polygon. And H, I'm going to mention the frequency curve. I am going to mention the cumulative frequency curve. J, I'm going to mention the stem and leaf plot, etc. So I've mentioned 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Whereas you were asked to not just mention, but explain 5 of them. So let's explain them one after the other. Starting with the pictogram. So I'm going to say the pictogram is a plot or graphical presentation of data using conventional pictures. Now, what do we mean by conventional pictures as it concerns the pictogram? The pictogram is when you use symbols such as humans, oranges, apples, as the case may be, to represent numbers. So let's say you have this to present let's say you have this to present where you have 20 and 10 in a certain year for boys, 20 boys, and let's put here a year to be 2001, 2002. I could represent this information using one human should represent 10 boys. And that will mean for 2001, it means I will have 2 humans. And for 2002, I will have just 1 human. Now, let's come over to the second one. The line graph is a plot of frequencies of data entries against the data entries using lines. As an example, you could have something like this where you have data entries 10, 20, 30, and so on. And you could have here to be 2001, 2002, and so on. Now, you could have boys in 2001 to be 20. So I'm going to drag this up to 20 with a line. And in 2002, you could have boys up to 10. And I'll drag it up to this point. So when you use lines in a plot of frequencies against data entries or time, you would end up having what we call a line graph. Now, for the box plot is a graphical representation of what we call the 5-number summary. So in the box plot, there's what we call the 5-number summary in statistics, and the 5-number summary comprises giving information on the minimum of a data set, the maximum of a data set, the first quartile, the median, and the upper quartile, of course, the third quartile. So when you produce a graph that displays that 5-number summary, you would end up having what is called a box plot. And the extremes usually are called whiskers. So the box plot looks like this. So it could be vertical, it could be horizontal. Let's say we have a vertical box plot. So it looks like this. It looks like this. So when you have a graph like this, such that this corresponds to Q1, the lower quartile, the middle here corresponds to the median, Q2, this corresponds to Q3, and this corresponds to maximum, and this corresponds to minimum. This kind of plot is called the box plot. Now, over to the bar chart. The bar chart is a plot of frequencies against data entries. Most times your data entries could even be years in question or under study using equally spaced bars. So for this occasion, you have something that looks like this. So if you plot frequencies against data entries or years or whatsoever, this kind of diagram is what a bar chart represents. Okay, it is a plot of frequencies against data entries. These data entries could be years, it could be any quantity at all being described, but please take note, it is represented by a diagram that looks like this, where you have equal spaces between bars. The height of these bars are proportional to the frequencies, and each of these bars represent commodities or items or data entries generally. Then comes the histogram. The histogram, unlike the bar chart, does not have equal spaces between bars. However, the histogram is a plot of frequencies against class boundaries. Now, please take note of a thing of this particular thing, that the histogram, unlike the bar chart, has no space between bars. So you end up having a diagram that looks like this. These are yet bars, but notice that there are no spaces between bars. Okay? Then comes the pie chart. Pie charts are sectored circles. Pie charts are sectored circles having angles or percentages that are proportional to the quantity or data entry being described. Okay, so what we mean by is a sectored circle is this. So for a pie chart, you have a circle that is segmented into sectors. Okay, these are sectors. Now each of these sector has an angle. Okay, and these angles, how large these angles are or how small tells a description on the quantity. So if this is rice, it tells you that if this is 20 degrees, for instance, then it means that 20 degrees is a description of the quantity of rice. If this is beans and this is 10 degrees, it tells you the quantity of beans. So we use angles or percentages proportional to the quantities being represented. Let's move over to the next one. So the next is the frequency polygon. Frequency polygons are plots of frequencies against class marks using lines. Okay? However, let's add to the list the second. However, frequency curves are plots of frequencies versus class marks. This time around, not using lines, but using curves. Let me show you an example. So if these are two diagrams, let's say this was our histogram. If you join the midpoints using lines, the midpoint of each bar corresponds to the class mark. But if I do same using curves, notice that this will be a frequency curve, this will be a frequency polygon. Why? I used straight lines in joining the midpoints, which are the class marks, and I used here curves joining the midpoints, which are the class marks. So for the cumulative frequency curve, this cumulative frequency curve is a plot of cumulative frequencies against upper class boundaries. So this defines what the cumulative frequency curve is. Here on the vertical axis, you would have cumulative frequencies, and on the horizontal axis, you would have upper class boundaries. Okay, so when you plot this curve, you would end up having something that looks like this. Okay, this kind of curve is called the cumulative frequency curve, a plot of cumulative frequencies against upper class boundaries. Let's go to the next and the final. Now, the last I'll be mentioning in this video is the stem and leaf plot. The stem and leaf plot is a representation of the data entries in a data set using a fragmentation of the digits, making each data entry into stem and leaf. For this, please take note, we have a diagram like this, where you have the stem and you have the leaf. And please see any video on stem and leaf for details on this. Remember, the focus is just to answer this question. Now let's go over to question 4, having answered question 3. Question 4 says, explain the terms unimodal data set, bimodal data set, and multimodal data set. So, unimodal data sets are data sets having just one mode. However, bimodal data sets are data sets having just two modes. Now comes multimodal. Multimodal data sets are data sets having more than two modes. So a trimodal data set could be called a multimodal data set, and a data set that has four modes or more can be called a multimodal data set. For question 2, we have the question: the data below summarizes the average scores of 50 students in MTH 1101. Using the data 1, obtain the arithmetic mean. So I'm going to quickly use the data. As you can see that data, please take note. I'm going to use this data now by doing the following. So I'm going to reorganize that table, putting average scores of students in MTH 1101, I'm going to call my XIs, and the number of students I'm going to call my FIs. So quickly, I now have XIs and FIs. So what I'm going to do quickly will be to put 15, 14, 12, 10, and 18. So these are my data entries, okay? Now, I'm going to put this to demarcate my total. So for frequencies, I'm going to put 12. I'm going to put 13, 8, 12, and then 5. Now, I'm asked to get my arithmetic mean by the normal computation. So the normal computation means that I'm going to have my arithmetic mean, or I rather, I'm going to have my arithmetic mean, x bar, computed as summation fi xi from I equals 1. Of course, there are 1, 2, 3, 4, 5 data entries to 5. Okay? I equals 1 to 5 all over summation fi from I equals 1 to 5. And this gives me summation fi xi. The next column I'm going to put here, I'm going to put here fi xi. Quickly, let's multiply. 15 times 12 is the first thing I'm going to multiply. 180. Then 14 times 13 gives 182. 12 times 8 will give us what? 96. 10 times 12 will give 120. And 18 times 5 will give us what? 90. So now, what would summation fi from I equals 1 to 5 give us? 50. So we'll have 50 here, and I'm going to put underneath 50. What would summation fi xi give us from I equals 1 to 5? 668. So I'm going to put here 668, and quickly one can see that the mean will be 668 divided by 50 to 2 decimal places. What would that give you? 13.36. Let's now move over to II. It says identify the modes and use your identification to categorize what kind of data set is provided. Looking at our data entry, we have 15, 14, 12, 10, 18. Now we have 10 occurring 12 times, 15 occurring 12 times, okay? Now, however, even though 10 and 15 occur 12 times apiece, you will notice that the data entry that occurs the most is 14, because it occurs 13 times. And that means, based on that, we can say our mode is equal to 14. And what kind of data set has one mode? It is a unimodal data set. And that answers that question, okay? Now let's move over to question 3. Question 3 says, obtain the 5-number summary by normal computation and sketch the box plot. Now, I told you something about the 5-number summary. The 5-number summary comprises, for number 3, the 5-number summary comprises the minimum. Now, what is the minimum in our data set? Obviously, the minimum is the smallest data entry amongst all these. So what is the smallest data entry? it is 10. So I'm going to write here 10. Now, what is our maximum? Our maximum is the largest data entry from amongst this list, which is 18. Now, remember, the 5-number summary comprises the minimum, the maximum, and it also has, what do you call it? The first quarter, the median, and the second quarter. So what we are going to do will be, I'm going to put a demarcation here, and I'm going to reorder this data. When trying to get the quartiles, please reorder your data for you to get precisely what you ought to get. So I'm going to put here my xi's again. Okay, so I'm going to rearrange my xi's starting from 10. I'm going to go in ascending order. 10 having a frequency of 12. Okay, 12. The next having a frequency of 8. Then the next one is 14 having a frequency of 13. Then the next is 15 having a frequency of 12. And the last is 18 having a frequency of 5. So that is what you do next. Then comes the next column. Once you've done this, introduce what you call cumulative frequencies. I'm going to call them CFIs. Okay? Introduce cumulative frequencies. Your cumulative frequencies in this case will now be 12. Being the first frequency will be the first cumulative frequency. The next will be 12 plus 8, which is 20. Being the second cumulative frequency. 20 plus 13 or 12 plus 8 plus 13 will give you 33, the next cumulative frequency. Added to 12, this will give you 45, the next cumulative frequency. And finally, adding 45 to 5 will give you 50. Okay? Notice that your final cumulative frequency is the same as your total frequency, and that shows you are correct. Now, your cumulative frequencies are ready. What can you do with them? So we are going to come over and use them to obtain the quartiles. Okay, so I'm going to put here, let's put a demarcation here and go with Q1. Q1 is also a component of the 5-number summary. So I'm going to put Q1 here. Q1 will be obtained as the n over 4th cumulative frequency value. Cumulative frequency value, okay, CFV. Now, your n, please take note, is your total frequency, which is 50. And 50 divided by 4 will give us 12.5, approximately 13. So this will give us approximately the 13th cumulative frequency value, which is equal to the 13th cumulative frequency value. How do you know it? It is, come to the cumulative frequency column. 13 is greater than 12, but not greater than 20. Since it is not greater than 20, trace from 20 down to your xi column. You will notice that the 13th cumulative frequency value is 12. And that means that 12 is your Q1. Okay? Now, if you did not arrange this in ascending order, you will get misleading results. So please endeavor to arrange in ascending order. Now comes Q2, which is your median. Your median is your Q2, and it will be the 2n over 4th cumulative frequency value. Now, that is more or less 1 over 2 times n, which is 25. So we are looking for the 25th cumulative frequency value. Now, come again. Once you get 25 here, please, this is not your median. You would come over here. 25 is greater than 12. It is greater than 20, but not greater than 33. Trace from 33 down to xi colon, it will give you 14. And that tells you that your median is 14. Then comes your Q3. Your Q3 being the upper quarter will be 3 over 4nth cumulative frequency value. Okay? Please, 3 times 50 is 150. 150 divided by 4 will give you what? 37.5, which is approximately 38 cumulative frequency value. Okay? Now, your 38 cumulative frequency value should be a value greater than 12, greater than 20, greater than 33, but since not greater than 45, it should be, when traced to the xi colon, it should give you 15. So it means this is 15. It now means that you've obtained your 5-number summary comprising our minimum to be 10, Q1 to be 12, Q2 to be 14, Q3 to be 15, and maximum to be 18. This is our 5-number summary. you can now plot your graph, that is your box plot, in this manner, where you would have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay? Then I could have gaps here of 1 unit. Okay? Now, since my minimum is 10, I could put this here using this 1 centimeter space. Then, since my maximum is 18, I would have it here using that same 1 centimeter space. Now, my Q1, 12, will come over here. Okay? And of course, the middle of this bar, I'm going to do this. My Q3 will be 15, so I'm going to come here in between 14 and 16 and put this as 15, and I will draw my rectangle and put the middle here. Okay, then my Q2 will be 14, which is this. And this gives you the box plot solving that problem. It's as simple as that. Let's move over to the next question. Now, to answer question 4, to display the line graph for the problem, all you have to do is this. So I would maintain 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and so on. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Now, please take note, I'm using a scale of 1 centimeter to 2 units. Okay? That's what I'm using on the vertical axis. Okay, so for the horizontal axis, data entry axis, I'm going to use a scale of 2 centimeters also. 2, 4, to represent 1 unit. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, to represent this. Now, please take note, for the plot itself, when xi is 10, your fi is 12. So I'm going to drag this to where I have 12 with a straight line. And remember, it's a line graph. For the case of 12 versus 8, when x is 12, fi is 8. I'm going to locate 12 and drag this up to 8. For a case of when x is 14, fi is 13. 14, I'm going to drag it to 13, which is the middle of 14 and 12, and 12 and 14. Then when xi is 15, which is from here, the middle of 14 and 16, we have when xi is 15, we have 12. So I'm going to drag it up to 12. So this will stop at 12. Then when xi finally is 18, we have 5. So I'm going to drag this up from 18 up to 5, the middle of 4 and 6 on the vertical axis. So you're going to have a graph that looks like this, okay? So this will be your line graph. Let's move over to question 3. Now, let's go over to question 3, where we are asked to use the data below to obtain the mean deviation. So what I'm going to do with that data quickly will be to put up this. So let's reorganize that data. So I have this as xi. Your xi in this case, please take note, will be the average scores of students in STA 1101. So I'm going to put here 12, 13, 18, 14, and then 16. I'm going to put that up. Then comes fi. Your fi's, you have your number of students, write it out as your fi's: 15, 10, 3, 17, and then 5. Now, we are asked to compute the mean deviation. Please take note that the mean deviation, let's call that number 1. The mean deviation, MD, in this case, since there are frequencies, will be given by the formula Fi xi minus x bar all over summation Fi. Quickly, you would notice that from I equals 1 to 5, of course, in this case, quickly you will notice that there is an x bar colon there. So it means we would have to compute our mean. So I'm going to introduce here a column for fi xi. In this column, let's multiply 12 times 15 will give us, and 13 times 10 will give us 130. 18 times 3 will give us 54. Then 14 times 17 will give us 238. 16 times 5 will give us 80. So summation fi will be equal to 50. Summation fi xi will give us 682. Now please take note, we will start with saying x bar, but x bar is equal to summation fi xi all over summation fi from I equals 1 to 5, I equals 1 to 5. And this will give you what? It will give you 682 divided by 50, which gives you what? 13.64. Now, please come over. Now that you've gotten your mean, the next thing you are going to do will be to compute xi minus x bar as you found it in the formula. So I'm going to create a column for xi minus x bar first of all. So xi minus x bar means 12, your xi minus your mean 13.64. What would that give us? Minus 1.64. Then 13 minus 13.64 will give us minus 0.64. Then 18 minus 13.64 will give us what? 4.36. Then comes 14 minus 13.64 will give us what? 0.36. Then 16 minus 13.64 gives us what? 2.36. Now, once you are done getting all these, you will now start multiplying each of them by your fi's. So fi times xi minus x bar colon comes in here. Now, 15, your first frequency times minus 1.64 gives you what? Minus 24.6. Okay? 10 times minus 0.64. Minus 6.4. Then 3 times 4.36. 13.08. Now note that once you get a result in two decimal places, you would have to add a 0 here to your previous result to make everything along a colon uniform. Then 17 times 0.36, 6.12. Then comes 5 times 2.36, 11.80. Okay, now let's start with adding the positive. 11.80 plus 6.12 plus 13.08 minus 6.40 minus 24.60. It gives you 0.00. Now, that means we now have our result for the mean deviation as 0.00 being your numerator divided by summation fi, which is 50. And your result obviously will be 0. Okay? Now, let's go to the second question, which says obtain the absolute mean deviation. The absolute mean deviation. The absolute mean deviation requires that we take summation from I equals 1 to 5 of fi times the absolute deviations from the mean, okay, divided by summation fi. So we will go back to the table. We will go back to the table and add more columns. So here, what we shall do will be to create a column for xi minus x bar. So create a column quickly for xi minus x bar. Okay. Now, after creating that column, the next thing you do is take the absolute values of your xi minus x bar column. Taking the absolute value of minus 1.6 will give you 1.64. Taking the absolute value of minus 0.64 will give you 0.64. This will come out as positive because the absolute value of a positive number is a positive number. So once you do that, we will now go over to a column called fi xi minus x bar in absolute value. So create this and let's get this done. So let's now multiply Fi, which is 15 times 1.64. This will give us the same result, 24.660 without the negative. So this will give us 10 times 0.64 will give us 6.40. And the rest will give us the same result, right? 4.36, 13.08, 6.12, and 11.80. When you use the frequencies to multiply this time around your absolute values. Yeah, okay? Now let's sum everything. 11.80 plus 6.12 plus 13.08 plus 6.40 plus 24.60. It gives you what? 62.00. So that will be your total. So you would come over and put here 62 divided 62.00 divided by 50, which is 1.24. Okay? So that becomes our result for the absolute mean deviation. Now let's move over to the variance. Now for the variance, we are going to start with recalling that number 3, variance, using the normal method, requires that you would compute S squared. I would suggest in this instance you use this formula from 1 to 5, Fi xi minus x bar all squared. Okay? To save you space in your table, all over summation Fi from I equals 1 to 5 in this case. Now, so it means you will quickly have to create a colon for xi minus x bar all squared. Create a colon for xi minus x bar all squared. So whatsoever we have as xi minus x bar, square them. Minus 1.64 squared will give us what? 2.6896. Okay? Minus 0.64 all squared. 0.4096. 4.36 all squared. 19.0096. Then 0.36 squared. 0.1296. Then 2.36 squared. 5.5696. Then you will now come over here and put here Fi xi minus x bar all squared, where you will multiply your frequencies with the sum, with the square deviations. Okay, so let's multiply this now. 15 times 2.6896, 40.344. Okay, then 10 times 0.4096. Good. 4.096. Then 3 times 19.0096. 57.0288. So I'm going to add a 0 here to make it uniform. Okay? Then comes 17 times 0.1296. 2.2032. Then 5 times 5.5696. 27.848. Okay? You have to add a 0 to make it uniform. Now, please add all these values. 40.3440 added to 4.0960 added to 57.0288 added to 2.2032 added to 27.8480. So what would that give us? 131.5200. So I'm going to come over here and say 131.5200 divided by summation Fi, which is 50, and this will give us what as our variance? 2.6304. And that will be our variance. Now, please take note, standard deviation in number 4 is the square root of variance. And That would mean taking the square root of 2.6304 to give us what? 1.62 approximately. Let's move over to question 4. Now in question 4, what we shall be looking at is the following. The question reads, for I, under question 4, in one sentence each, explain the difference between the terms correlation and regression. So let's get that done. For the difference between correlation and regression, I'm going to do this. So I'm going to write here correlation, and I'm going to write here regression. Now, so both of them are concepts in statistics. So I'll start with saying correlation is a concept in statistics that describes the relationship between variables, especially with regards to the strength or weakness of the variables using what we call a correlation coefficient, using a correlation coefficient. Okay? So this is basically what happens in the concept called correlation. However, in the concept called regression, regression is also a concept in statistics. So regression, on the other hand, is a concept in statistics that models or describes the pattern of relationship, the relationship between variables. Okay? So this is the major difference between these two concepts. Let's go to the next question. The second question says, under question 4, subdivide bivariate correlation into two groups and pictorially describe 5 possibilities under both groups. Let's get that done. So, bivariate correlation, that is the correlation involving two variables, okay, is subdivided into A, linear bivariate correlation, and B, non-linear bivariate correlation. So these are the two groups we are asked to subdivide bivariate correlation into. Now, I'm going to put here linear bivariate correlation. Okay? And I will illustrate linear bivariate correlation. And over here, I'm going to put non-linear bivariate correlation. Okay? So let's use pictorial representations to differentiate these. That is to know the 5 classes. Now take note, let's have this, let's have this, and let's have this as 3 plots: y, y, y versus x, y versus x, and y versus x. Okay? Now, if there is a linear bivariate correlation between two variables, y and x, it is possible that the plotted points could be scattered all around such that we cannot tell if there is a relationship, whatever, existing between y and x. In this case, we say we have a zero linear bivariate correlation. Zero linear bivariate correlation. Now, if it so happens that the plotted points appear to follow a straight line, such that the straight line shows that as y values increase, X values are also increasing. Then we would call this a positive linear bivariate correlation. Then if it so happens that our plotted points appear along the direction, a downward direction for Y, whereas an onward direction for X, then we say we have a case of a negative linear bivariate correlation. Simply because linear in the sense that it is actually following a straight line pattern, bivariate in the sense that it involves two variables, Y and X, and that is for the linear bivariate correlation. Coming over to the nonlinear bivariate correlation, nonlinear bivariate correlation, we have two cases, this and this, such that you could have Y again, two variables, Y and X, and it could happen that the plotted points appear to follow a curve-like pattern, such that the curve-like pattern is convex. In this case, we say there is a positive nonlinear bivariate correlation. And if it so happens that the reverse is the case, that you have a concave curve-like pattern, then we say that the correlation between Y and X is a nonlinear bivariate correlation that is negative. Now let's go over to III of question 4 that says list any four properties of the correlation coefficient R. III. So number 1, let's call A. We have that -1 is less than or equal to R less than 1, telling you that correlation lies between -1 and 1. B, you have that R could be equal to 1, and in which case we have a perfect positive correlation. We have C, R equals -1, describing a perfect negative correlation. We have R equals 0, implying that this is a case of zero correlation, no correlation. You have a case of E, where R lies between 0 and 0.5. Okay? And in this case, we say that the correlation is positive but weak. And if R lies between 0.5 exclusive but 1 inclusive, then we say it is positive and strong. If R lies between 0 and -0.5, we say that it is negative but strong. And H, if R lies between -1 and -0.5, we say it is negative and weak. So you can pick your properties from any of these, and let's move on to the next question. It says using the average scores of students in STA 1101. Now quickly, I'm going to recall that we had our average scores in STA 1101, which we had called our Y previously. You can go back in the video to see STA 1101. Recall we call this our YI. Okay? And MTH 1101, recall that we call this our XI. Now, we are told using the average scores of students in STA 1101 and MTH 1101, obtain their A, product moment correlation, and B, rank correlation, accompanied by accurate interpretation. So what I'm going to do will be, please go back to the questions that involve this table. Okay? So I'm going to bring out the data as it is in the question. For STA 1101, we had 12, 13, 18, 14, 16. For MTH 1101, we had 15, 14, 12, 10, 18. Okay? Now the next thing I'm going to do, since we want to compute the first correlation we were asked to compute is Pearson's correlation or product moment correlation, right? So I'm going to do this because of what the formula contains. I'm going to write out the formula for product moment correlation coefficient, otherwise called Pearson's correlation coefficient. So I'm going to write it out as R equals n summation from I equals 1 to n xi yi minus summation xi from I equals 1 to n times summation from I equals 1 to n yi all over the square root of n summation I equals 1 to n xi squared minus in brackets summation from I equals 1 to n xi all squared times the square root of n summation from I equals 1 to n yi squared minus summation from I equals 1 to n yi squared. So I'm going to write out the formula first, okay? And then this formula will guide me on what to get done in my table. So let's go over to the table now and do the following. So from the formula, it is obvious we need a product of x and y. So x, I, y, I is what I'm going to call this column. From the formula, it shows us that we need a column for xi squared. I'm going to put this down. From the formula, it shows us that we need a column for yi squared. I'm going to put this down. Okay? Now, let's get the following. 12 times 15 gives us what? 180. 13 times 14 gives us what? 182. 18 times 12 gives us what? 216. 14 times 10 gives us what? 140. 16 times 18 gives us what? 288. Then let's go over to xi squared. 15 squared under xi squared. 15 squared will give us what? 225. 14 squared will give us what? 196. 12 squared will give us what? 144. 10 squared will give us 100. 18 squared will give us 324. Now let's go to y squared. Y squared is where you compute the square of each value on the y. So 12 squared will give us 144. 13 squared will give us 169. 18 squared will give us 324. 14 squared will give us 196. And 16 squared will give us 256. Okay? Now, once we've gotten our values, we would come over and compute the following. So I'm going to do this. N is 5 because there are 5 data entries under each variable. Summation xi, yi. We are going to add all these. Let's quickly add this. All these 180, 182, 216, 140, 288 under xi, yi gives us what? 1006. Then when we add all the values under xi, what do we get? 989. When we add all the values under yi squared, what do we get? 1089. Okay, now we are going to bring those values here to now have 1006 minus in bracket summation. Let's add all the values under xi. Add all the values under xi. What are we going to get for summation xi? 69. Add all the values under yi. What are we going to get for 73? So you do that addition and confirm. So we are going to have here 69, and in brackets here we are going to have 73 all over the square root of, this will be 5 times the sum of all xi squared, 989, minus the sum of all xi's all squared, that is 69 squared. So then we will come over to the next square root. This will be 5 times the square, 5 times the sum of all yi squared, 1089, minus the sum of all y's squared, which will be 73 squared. Now let's come over here to finish that problem. So we have R equals 5 times 1006 will give us what? 5030 minus 69 times 73 will give us what? 5037 all over. Coming over here, we would have the square root of 5 times 989 gives us what? 4945 minus 69 squared gives us what? 4761 times the square root of 5 times 1089 gives us what? 5445 minus 73 squared, 5329. Now, if you simplify further, what are we going to get as our R value? The numerator will give us minus 7 all over the square root of what times what? 184 times 116. And that gives us our final answer approximately as what when simplified? Minus 0.048. So you simplify that and confirm that value. Now let's come over to the rank correlation coefficient. So for the rank correlation coefficient, we would maintain our values, X and Y, and we would come over here and do the following. So the first column we are going to put here will be the rank of the Y values. Let's rank the Y values. Please take note, the highest value will carry a rank of 1 and you proceed accordingly in that manner. So the rank of the Y values will be 18 carries 1. The next value is 16, 2. The next value is 14, 3. The next value is 13, 4. The next value is 12, 5. I would now come over to the ranking of the X values. Ranking of the X values implies that 18, the highest, will carry 1. 15 will carry 2. 14 will carry 3. 12 will have 4. And 10 will have 5. Now, the next column will be the column we call the DI column, where you subtract the ranks. Okay? So here we would subtract the ranks. And this will give us 5 minus 2, 3, 4 minus 3, 1, 1 minus 4 minus 3, 3 minus 5 minus 2, and 2 minus 1, 1. Now here we would square whatsoever we had as our DI, and this would give us 3 squared as 9, 1 squared as 1, 3 minus 3 squared as 9, minus 2 squared as 4, and 1 squared as 1. Adding all this will give us our summation DI, and what would that be? 24. So we will now come over and put here the rank correlation coefficient will be 1 minus 6 summation from I equals 1 to n DI squared all over n into bracket n squared minus 1, and this will be 1 minus 6 times what our DI squared is 24 all over 5 times 5 squared minus 1. And this will be equal to 1 minus 6 times 24 gives us what? 144 divided by 5 times 25 minus 1. 25 minus 1 is 24. 25 minus 1 is 24. 24 times 5 will give us 120. Now, simplifying this, we will end up having our result as minus 0.02. Now, please take note, the question does not end here. You will notice for the rank correlation coefficient and the Pearson correlation coefficient, otherwise called the product moment correlation coefficient, we got both results to be negative and very, very small, the value of the correlation coefficient. So what would our interpretation be? We would therefore say that R is negative but strong. Why is our conclusion so? It is because the value of R is very close to 0. Since it is very close to 0, but from the left, it means it is negative. But since it finds itself between 0 and minus 0.5, it means it is strong. Okay? So this will be your interpretation. Let's go to question 5. Now let's go to question 5, where we shall describe question number 1. Define the terms skewness and kurtosis. Skewness is the degree of asymmetry or departure from symmetry of a distribution. Okay? So this defines skewness. the degree of asymmetry or departure from symmetry of a distribution, whereas kurtosis is the degree of thickness of a distribution, often taken relative to the normal distribution. Okay, that answers question 5I. The next question, II in 5, says, with the aid of neatly well-drawn accurate diagrams, describe the types of skewness and kurtosis. So I'm going to put here, so under skewness, I'm going to do the following, and under kurtosis, I'm going to do the following. Okay, so if a distribution is skewed, then it means we could have it as being left skewed, in which case you would have something like this. There will be symmetry on one side, and on the other side you have a long tail. So this will be called left skewed or negative skewness, okay, because the tail is to the left. Now, however, it is possible that it could be skewed to the right, where you have this normal, to the right where you have a long tail. So we say this is right skewed or positively skewed. Now, the last is that the distribution may be normally distributed, in which case you have this. So in this case, we say it is normally distributed. There is no skewness, normally distributed. Okay, so these are the three possibilities under skewness: left skewed, right skewed, normally distributed. Now coming to kurtosis, the degree of thickness of a distribution, you could have a case like this, a case where it is peaked upwards, so peaked upwards, we call this a case of leptokurtic. Then we have another case called the case of platykurtic, in which case you have the top flat, and we also have the case we call mesokurtic, otherwise called normal distribution or normally distributed. So these are the possibilities under skewness and kurtosis. Let's go to the next question. Now let's go to question 3 of number 5, which demands that we find the standard deviation. Okay, so using the data in question 2, please, not question 1. So recall that the data in question 2, I'm going to reorganize it at once, is such that the average scores of students was taken to be our xi, and our fi's were taken to be the number of students. So I'm going to bring out that data here. 1, 2, 3, 4, 5. So I'm going to call this 15 as we have it, 12, 10, and 18. Please go back to the data in question 2 to see the data I'm using. So we have 12 here, 13, 8, 12, and of course 5. Now, the next thing I'm going to do will be to get the mean. For you to compute the standard deviation, we'll be needing the mean, okay? Since I'll be using this formula, I'll write below. So let's compute the mean. The mean is FIXI. So 15 times 12 will give us what? 180. 14 times 13 will give us what? 182. 12 times 8 will give us what? 96. 10 times 12 will give us 120. 18 times 5 will give us what? 90. Now, once I get that done, I'm going to add up all my frequencies. What would adding my frequencies give us? 50. What will adding the FIXIs give us? 668. And immediately I will write here x bar, my arithmetic mean, is summation from I equals 1 to n, FIXI. In this case, our n is 5. all over summation fi from I equals 1 to 5. And here I would have 668 divided by 50, which gives us what? 13.36 approximately. Okay? Now, having gotten that, I will create a colon. For you to get your standard deviation, you must first of all get your variance. So I'm going to compute xi minus x bar. Xi minus x bar means subtracting from all our xi values the value we've gotten to be our mean. So 15 minus 13.36 gives us what? 1.64. 14 minus 13.36 gives us what? 0.64. 12 minus 13.36 gives us what? Minus 1.36. 10 minus 13.36 gives us what? Minus 3.36. 18 minus 13.36 gives us what? 4.64. I will compute the next column, bracket xi minus x bar all squared. So let's compute that. What would that give us? Xi minus x bar all squared will give us what? 2.6896 for 1.64 squared. 0.64 squared gives us what? 0.4096 minus 1.36 squared gives us what? 1.8496 minus 3.36 squared gives us what? 11.2896. Then 4.64 squared gives us what? 21.5296. Now, adding all this will not be the case. Now, the next thing to do would be to multiply our fi's with xi minus x bar all squared. So create a colon for that and get this done. So multiplying 12 and this particular colon gives us what? This particular cell, 32.2752. Multiplying 13 and 0.4096 gives us what? 5.3248. Then multiplying 8 times 1.8496 gives us what? 14.7968. Then 12 times 11.2896 gives us what? 135.4752. 5 times 21.5296 gives us what? 107.6480. Now, adding all this to this to this to this to this gives us what? 295.52. Okay, so I'm going to add 2 zeros here. 295.5200. Okay, now I will bring out my formula. S squared, which is the variance, is summation from I equals 1 to 5. In this case, fi xi minus x bar all squared all over summation fi from I equals 1 to 5. And this will give us 295.5200 divided by 50. And that will give us what? 5.9104. Now, since standard deviation, which they want us to find, is the square root of variance, which is the same as the square root of what we've just obtained as our variance, 5.9104, this will give us what approximately? 2.4311. So that will be our standard deviation. Let's go over to question 4. Now, let's move over to question 4, where we are asked to deduce the Pearson's first coefficient of skewness and moment coefficient of skewness. Now, please take note, for us to get this done, we have to reconstruct our table to do the following. So I'm going to go back to the table and bring up the following. So let's reorder our table, arranging our x values in ascending order. So we have our x values to be, the smallest value is 10 with a frequency of 12. The next value is 12 with a frequency of 8. The next value is 14 with a frequency of 13. The next value is 15 with a frequency of 12. The next value is 18 with a frequency of 5. Now, of course, our sum gave us 50. Now, coming over here, we shall put the cumulative frequencies. Why do we need this? It is simply because it will help us ensure that we get our median and our mode correctly. So what I'm going to do now will be to put up 12 being the first cumulative frequency. Since the first frequency is 12, the next is 20, 12 plus 8. The next will be 20 plus 13, giving us 33. The next will be 33 plus 12, giving us 45. The next will be 45 plus 5, giving us 50. And this shows we are correct because the last cumulative frequency and the last cumulative frequency and the total frequency are the same. So the Pearson's first coefficient of skewness is given as skewness equals the mean minus the mode all over the standard deviation. Recall that we had our mean to be what? 13.36. And our standard deviation, we got it to be what? 2.4311. Minus, now, let's come over to the table and get our mode. The mode is the data entry that has the largest frequency. Looking at all these data entries, 10, 12, 14, 15, 18, the one that has the largest frequency of 13 is 14. So 14 is our mode. So what will 13.36 minus 14 divided by 2.4311 give us? Minus 0.2633 approximately. Okay? Now, this gives us our result for Pearson's first coefficient of skewness. So, now to compute the moment coefficient of skewness, the formula is alpha equals m3 over s cubed, which will now be what we have to find. And we are going to recall that m cubed is summation fi xi from I equals 1 to n of xi minus x bar all cubed all over summation fi from I equals 1 to n. Now, what you have to do in this case will be to get the values of x minus s all cubed. So this 0.14 all cubed will give us what? 4.410944. This will give us 0.262144. When you cube this, you're going to get minus 2.515456. When you cube this, you're going to get minus 37.933056. When you cube this, you're going to get 88.716536. Okay? Now multiply each of them by the frequencies, and that will give you for this 52.931328. The next one, when multiplying the frequency, will give you 3.407872. When you multiply this by this, you're going to get minus 20.123648. When you multiply this by this, you're going to get minus 455.196672. And when you multiply this by this, you're going to get finally 443.58268. Now, summing all these up will give you 24.60156. Now, quickly, you will see that 24.60156 divided by 50, which is summation fi, will give us 0.4920,312. Now, if you bring that value over here, 0.49320312 divided by s cubed, which is 2.4311 all cubed, what we got earlier of our standard deviation. When you divide this, you're going to have your result approximately at 0.034. And that concludes this problem. So for question 6i, we are going to start with defining the index number. Please take note that index numbers are statistical measures that describe the change in the value of a variable or group of variables with respect to time, geographical location, or some other quantity, some other measure, okay, or quantity. Now, the next question says, define the term base value. So please take note that base values are values of reference with which one computes index numbers. They are values of reference with which one computes index numbers. Now, they may be fixed base values. They may be fixed base values or linked base values. So they are either fixed base values or linked base values. Now, please take note that fixed base values are values that do not change when used for computing index numbers. Linked base values are base values that successively change in computing index number. So linked base values successively change in computing index numbers, but fixed base values do not change when used to compute index numbers as your values of reference. Let's go to the next question. Now let's go to III. So let's define price index. Let PI be the price at TI and let P0 be a base value. Then the price index PI will be defined as PI over P0 times 100. Next, let QI be the quantity at TI for any commodity at all, and let Q0 be a base value. Then we say QI will be equal to QI over Q0 times 100. Now finally, let PI QI, which is equal to VI, be the value at TI, a time TI, and let V0 be the base value. That is, in all, we are referring to fixed base values. Then VI will be equal to, that's the value index will be equal to small vi over V0 times 100. And that completes this question. Finally, let's go to question 4. Using the formula in question 3, we can now compute the following. So we are asked to do this. We have years 1, 2, 3, 4, 5. Next, we have quantities, QI, given as 12, 15, 10, 5, 10. We have PI, prices, given as 40, 60, 80, 50, and 30. Now, we are asked to compute VI, that is the product of this and this. So what will 12 times 40 give us? 480. 15 times 60 will give us our VI. What does that give? 900. 10 times 80 will give us what? 800. 5 times 50 will give us 250. 10 times 30 will give us 300. So once you are done computing this, we now go to the quantity index. Quantity index is QI. For you to compute the quantity index, this question says you should use year 2 as your reference fixed base value. So all the values here will be our reference fixed base values respectively. For quantity index, this will be 12 over 15 times 100, and that gives us what? 80.00. Then 15 over 15 times 100 gives us 100. Then 10 over 15, the base value times 100 gives us what? 66.67. Then 5 over 15 times 100 gives us what? 33.33. Then 10 again gives us 66.67. We now move over to the price index. Now for the price index, come over to the price column. We are using 60 as our base value. 40 over 60 times 100 gives us what? 0.67. 60 over 60 gives, times 100 gives us what? Then 80 over 60 times 100 gives us what? 133.33. Then 50 over 60 times 100 gives us what? 33. 83.33. Then 30 over 60 times 100 gives us what? 50.00. Now finally, coming over to the last one, which is the value index. The value index, in this case, our base value is 900. So 40 over 900 times 100 gives us what? 53.33. 900 over 900 times 100 gives us what? 100. 800 over 900 times 100 gives us what? 88.89. Then 250 over 900 times 100 gives us what? What? 27.78. Then 66, 300 over 900 times 100 gives us what? 33.33. Thank you for watching this video. Please like, share, and subscribe. I'll see you in my next video.